As a second example, the price of a stock follows a geometric Brownian motion with parameters mu is equal to 0.12 and sigma is equal to 0.24. If the present price of the stock is ₹40, what is the probability that a call option having 4 months to exercise time and with the strike price k is equal to ₹42 will be exercised? So, a call option on a stock with the exercise time t and a strike price k is in the right, but not the obligation to buy a certain number of shares at time capital T for a fixed price k, because the call option is the right but not the obligation to buy. That's the meaning of a call option. If S of t denotes the market price of this number of shares, then the value of the option at time t is the value of the option S of t minus k if S of t is greater than k. That is, if the value of the price is greater than k, then the value of the call option is S of t minus k. Since the share can be bought for a k and immediately sold in the market for S of t. On the other hand, the option is worthless and will not be exercised if S of t is less than or equal to k. The call option is a right but not the obligation to buy. Hence, if S of t is greater than k, then the value will be S of t minus k. The value will be 0, or the option is worthless and will not be exercised if S of t is less than or equal to capital K. Hence, the question is, what is the probability that the call option having a 4 months to exercise time with the strike price k will be exercised? That means the required probability is what is the probability that S of 1/4 is greater than 42, because k is 42 and the time is 4 months, whereas the all other values are in years. You can assume these parameters are in years. Therefore, 4 months will be 1/4. 4 months will be treated as a, so here it is given for, so the probability of S of 1/4 is greater than 42 will be the required probability. So we are not computing actual probability, because you can use the earlier concept, because S of t follows a log normal distribution. So using the log normal distribution, one can find the probability of S of this greater than 42. As a remarks, we know that Wt is a Brownian motion, and the increments are independent as well as increments are stationary, and Wt is normally distributed with the mean 0 and the variance t if it is a standard one. If it is not a standard one, then the Wt is normally distributed with the mean mu times t and variance is sigma square t. While the x of t, here it is, the x of t is a log normal distribution, because it is x of t is x of 0 e power Wt. Hence, x of t is a log normal distribution. So that is a relationship between the Brownian motion and the geometric Brownian motion. In the Brownian motion, each random variable is normally distributed, whereas in the geometric Brownian motion, each random variable is log normal distribution. Therefore, you can use the central limit theorem, as a sum of random variable will tends to again normal distribution if they are independent. But here, since x of t is a log normal distribution, you can use those properties with the product. So that's the second one. The product of independent log normal distribution is also log normal distribution. So the way we use the sum of independent normal distribution is a normal distribution, and the normal distribution and the log normal distributions are connected in the form of x of t is equal to x of 0 e power wt. Hence, the product of independent log normal distributions is also a log normal distribution. Hence, suppose you have an independent geometric Brownian motion. If you make a product, then that is also a geometric Brownian motion. The third remarks, it removes the negativity property. Means the Brownian motion has the range minus infinity to infinity. Since we made x of t is equal to x of 0 e power wt, the range of x t is 0 to infinity, it removes the negativity property. Also, it justifies from the basic economic principles as the reasonable model for stock prices in a real non-arbitrage world. Hence it removes the negativity problem, or it takes the non-negative values. It justifies from the basic economic principles as the reasonable model for stock prices in an ideal non-arbitrage world. Finally, we are presenting a process derived from the Brownian motion. This is not the derived one, but this is a very generalized stochastic process comparing with the Brownian motion and the geometric Brownian motion. This has a lot of applications in finance. The definition: a stochastic process x of t is said to be a Levy process if it satisfies the following properties. The first property, x of 0 is equal to 0. The same property we have used when we define the Poisson process, when we define Brownian motion also. So here also the Levy process, it satisfies the properties x of 0 is equal to 0. The second property, for t greater than 0, xt is almost surely continuous. So if you see the sample path of x of t, it is almost surely continuous. The third property, for 0 less than or equal to t naught, less than t1, less than t2, and so on till less than tn, for all n, the increments, that is x of ti minus x of ti minus 1, for I varies from 1 to n, the increments are independent as well as stationary. This is true for all arbitrary n time points, for all n. The fourth condition, for a greater than 0, the probability of in absolute of x of t minus x of s greater than a will tends to 0 as t tends to s. So if these three properties are satisfied by any stochastic process, then that stochastic process is said to be a Levy process. Any stochastic process satisfying these four properties will be called it as a Levy process. One can observe the Poisson process and the Brownian motion are the examples of Levy processes. The Poisson process is a continuous time discrete state stochastic process, whereas the Brownian motion is the continuous time continuous state stochastic process. The Brownian motion, the sample path or right continuous, because if you see the sample path, the inter-arrival of events are independent and they are exponentially distributed with the parameter lambda. Therefore, whenever some event occurs, the sample path that increment with the unit and it says the same value till the next event occurs. So in the levy process, the property is for t greater than 0, x of t is almost surely continuous. So that includes the sample path is continuous as well as the sample path is right continuous. Hence, the property we discuss in the Poisson process for the sample path as well as the property discussed in the Brownian motion for the sample path, both are satisfied by saying x of t is almost surely continuous. The first property is used in both Poisson process and the Brownian motion, because suppose n of t is a Poisson process, then n of 0 is equal to 0. The Brownian motion is a Wt, then the W0 is equal to 0. So the first property is the same for Poisson process and the Brownian motion, whereas the second property, the sample path of Poisson process are right continuous functions, whereas the sample path of Brownian motion are continuous functions. The third property is the same in both Poisson process and the Brownian motion, because both the places we have the third property, the increments are independent as well as stationary for all n. We won't discuss what is the distribution of the increments in the third property. We discuss only the increments are independent and stationary. Whereas in the Poisson process definition, we give the fourth property as the increments are Poisson distributed random variable with the parameter lambda times t minus s, where Wt minus Ws is the increment or s is less than. Whereas in the Brownian motion, we say we supply the fourth property as the Wt minus Ws is the increment, which is normally distributed, normal distributed random variable with the parameters mu times t minus s and variance sigma square t minus s. For the standard Brownian motion, the mu is equal to 0 and the sigma square is equal to 1. Whereas here, for a greater than 0, the probability of in absolute x of t minus x of s greater than a will tends to 0 when t tends to s. So this property is valid both for Poisson distributed random variable in the Poisson process as well as the normal distributed random variable in the Brownian motion. Hence, Poisson process and Brownian motion are the examples of levy process. So this is a more generalized stochastic process when you are comparing with the Brownian motion and the geometric Brownian motion. So in this lecture, we have covered the definition of a geometric Brownian motion and the important property, that is a Markov property of a geometric Brownian motion. And then we have discussed applications of geometric Brownian motion, how one can use the geometric Brownian motion to model the stock price. And also we have given two examples. Finally, we have discussed the levy process, the definition as well as the standard examples of a levy process. So with this, we are completing the lecture 2 processes derived from Brownian motion. Here is the list of references.